Okay, I'm going to demonstrate today this HP 16500B logic analysis system with, it has oscilloscope and logic analyzer modules in and various other features. So I'll start by switching on, excuse all the various fan noises and drive noises and things. The camera's pointing just at the analyzer's screen. Sorry about any flicker, that's due to the camera, not the screen itself, which is perfectly steady. See, it passes all its self-tests at startup, apart from it says no disk in the floppy drive, which is perfectly true. It's now setting itself up, loading its various modules and doing calibration and so on. It should fire up okay. Copyright 1992, old but good. And we have here the main home screen where you can see the various functions. The top card I've got in the slots is an oscilloscope card, 2 gigasamples per second, and then the bottom two slots are occupied by 96 channels, I believe, of logic analysis. Each one has 3 cables which are 16 channels each. It might even be more than that. Refer to the description for more details. I think they might even be 96 channels each, so there's 192 channels of logic analysis, but check what I've double checked and written down. We've also got configuration here for communications, Ethernet and the printer, if you would wish that to be used. And I'm just going to take you through some of its features. First of all, nicely for this, it has an Ethernet interface, which I've not got connected to anything at the moment, but you can set its IP address and so on here, it all works fine. You can FTP files in and out of it and use X to remote control it and that sort of thing, which is very handy. So you press the X window button and it will connect to a server and you can operate it. Printer, you can choose what kind of printer you want, an HP ThinkJet or LaserJet, PaintJet, lots of other types of jet. Notice it's all driven by a touch screen, which is very handy. There's also a selector knob on the right here, which is just out of the camera's view. First of all, I'm going to go through the configuration. We've looked through the modules. There's a hard drive in here, which opens up. This is the original IDE hard drive. I can't provide any guarantee, but it's worked fine for all time I've owned it. Down the bottom here, total capacity 210 megabytes, which should be more than enough for anything that you wish to do with this machine. I wouldn't recommend using it as a file server though. You can store on here saved results from various tests and things. I often use it for saving configurations of the modules for particular operations, and I've got a few set up to show you here. But before we go any further, we'll go into the test thing just to show that everything is working. So if I load the test system, which takes a moment or two, it's loading all the test modules, and here we go. The screen's changed colour, it's now brown instead of blue. So if we go, let's start with the mainframe. No, let's not do the mainframe test because it did that at power up and you saw it pass. Let's do the oscilloscope test and press the test button. Run all tests. Data memory, time base, A to D converter, D to A converter, trigger test and inter-module bus test have all passed, so that's all good. We'll go into the logic analyzer test. If I just run everything, 0, 1, 2, 3, 4 and 5, all passed, all good. And if you press the data input inspection, it shows that all the inputs are working. In fact, we can see how many inputs there are here: 16, 32, 64, 96 on each pod. So there's 192 channels on this beast, should you wish to connect them all up. You can see they're all showing activity and they're all working. So now, having done the tests, let's show some of the modules in action. I'll exit the test system, go back to the main screen. So first I'm going to demonstrate the oscilloscope module. I've got a couple of configurations all set up on the hard drive, so just to save a bit of time. So we will first go in and use just an ordinary probe to demonstrate how the scope module works. It's effectively rebooting now, which is why it takes a moment or two. Here we go. So we go to the oscilloscope module in slot A. First of all, no, wrong button. I want to go to hard drive and load the configuration for this one, this is just something I've set up earlier. So we'll load the scope from this file probe, which I've just set up before doing this demo, and that's loaded. And now we go in here. Okay, so it's even got the data from when I was testing it earlier on. As you can see, there's a square wave on the screen. So I've got this scope module has two inputs. I've got one of them connected to a probe which is connected to a simple square wave generator, and I will just set that running right now. Oh yeah, now you see its little party trick. It says failed interpolator cal sometimes, not always. That doesn't seem to affect normal operation. There just seems to be a few hundred picoseconds of jitter on the trace, but that doesn't seem to actually matter. I've been using this thing quite happily for 5 years or so without any problems, but occasionally you get that little yellow message. So here we have a square wave being updated on the screen, and I can do the usual scope things. If I can use the knob here to change the scaling, 400 millivolts per division, 1 volt per division. It goes in a 1-2-4 sequence because it's kind of a digital beast. You can change the offset to move it up and down like this. It perhaps isn't the fastest to respond, but it's perfectly usable in a lab environment, especially if you're setting up tests between analog and digital world, which this is great for because it can do inter-module measurements. We can change the time per division, see more cycles. It all works fine. We can fiddle around with the labels of the channel. So, we can give that one a thing, let's call it, oops, we can use the touch screen to label it. We'll call it square, oops, can't even spell, never mind, done. So there we go, it shows that A1 is called square on the screen there. And we can do auto measurements. There we go, it's showing the frequency of 100 kilohertz. Oh, it's actually measuring the wrong input. If I press input A1, now it's measuring 1 kilohertz, 400 millivolts peak to peak, which is roughly as it should be. So it does all the things you'd expect of a digital scope of the era, but it has 2 gigasample per second sample rate, which is really good, and reasonably long record length of 32K. What I'm going to do now is show the scope's bandwidth by measuring the rise time of a very fast edge. For that, I will go back and load a different configuration, which I've got set up here. Rise time, rise, there we go, execute that one. That's loaded. We'll go back to the oscilloscope, and so this, I've got the other input on the scope connected to this fast rise pulse generator, which gives this edge here, and I'll just run again just to show you that it works. There we go, it's captured that, and we can do that as many times as we like. And the auto measure is set here and is giving a rise time of 560 picoseconds, which by the usual mathematical sleight of hand, divide that into into sort of 300 or so, and you get some idea of the scope's bandwidth. It's rated at 500 megahertz, but it seems to exceed that quite happily in practice. So it's really a very fast scope indeed, and works very nicely. So that's the oscilloscope module working. I could show, in fact, just for fun, show both traces at the same time. Let's put that one on as well. Actually, no. We can you can change all the way, all sorts of math functions with the channels. Let's overlay channel 1 as well, and we've got channel 1 running. So I'm displaying both channels at the same time. There's a way. Channel mode, overlay. So you can get them both on the same screen. So if I insert channel 1 and channel 2, there we go, we get them both at the same time. You can see the blue and red lines are together. And if I run that repetitive and slow the time base down a bit, you should be able to see both channels have signals on. There we go, you can see my square wave at the bottom there, it's triggering on the wrong one, but anyway, you get the general idea. We've got both channels working. And now to move on to the logic analyzer, which is also fun. Excuse me, back the camera there. I will just load a file called demo into the logic analyzer slot. Yeah, demo done. Execute that. Okay, that's loaded. I don't know if you can see there's a little star that flashes in the corner while it's accessing the disk. And we go to the logic analyzer. There we go. And this is showing all the pods. I've got, there's all sorts of clever features in here. You have to read the manual. I've just got pod E1 connected with 8 bits connected to a simple counter output on a computer, and it's analysing the timing of that. So for example, if I go to the waveform display, there is the counter, and just to prove there's nothing up my sleeve, I'll stop that and run again. There's nothing there. If I run repetitive, see there's nothing there, but if I start my counter again, up comes the signal, and here we can do the usual things, zoom in and out. There's all the captured data, and you can do all manner of logic analysis on here. It's got clever triggering functions, so you can look for particular combinations of signals. For example, we should, if I'm feeling bold, trigger if I trigger on A. Okay, so we just have to set conditions. There's massive numbers of possibilities for triggering, counting edges, catching glitches, all sorts of things in here. I can never remember how to drive this. I always just go and read the manual. But that's the... Oh, look, A, we can define what A means. There we go. A is set. Okay. So A is when it matches a particular... so yeah, we're setting a macro here. So trigger type A is when the input hits a particular number. So I don't know, we'll trigger on 5 or 4A, let's say. So we're looking for that hex number, and we're going to trigger when that is present for more than 80 nanoseconds. So now we'll run. Now you see the display is stable. It's actually triggering on the moment when our counter reaches hex 4A. And we can, for example, display the listing, and there is the absolute listing, and we can scroll backwards and forwards through it. There we go. There's at 0 point on the trigger. There's 4A, and it, the counter is going upwards and upwards to 4B, 4C. So you can search for things in the digital data and do all sorts of clever stuff. But this video just shows that the machine is basically in working condition. That's about it. You can see it's got today's date and time on there, just to prove there's nothing up my sleeve. And that completes the HP 16500B logic analysis system demonstration. The cards in here are 16534A for the oscilloscope and 16550A for the two logic analyzer cards, and there is also a 16500L interface which gives you the Ethernet. Thanks for watching.